Bueno, la doctora Angeluccetti es máster en Ingeniería Ambiental y Territorial y tiene un doctorado en Gestión y Protección Ambiental en la Universidad Politécnica de Torino. Además es especialista en sistemas de información geográfica en un instituto de investigación, en un instituto dedicado a la transferencia como es ITHACA, como ya podéis ver directamente en pantalla, produciendo ya más de 10 años de trayectoria profesional y trabajando básicamente en detección de sequías y monitorización mediante técnicas de teledetección, por tanto de satélite, datos satelitales, proyectos relacionados con Big Data, vulnerabilidad a inundaciones y también da apoyo a lo que sería pues, un Global Land High Resolution Hotspot Monitoring within the Global Land Component of the Copernicus Land Service, que es ahora mismo el trabajo principal que está desarrollando la Unión Europea a nivel de teledetección. Desde 2008 a 2010 trabajó también en África, por tanto en proyectos de cooperación y desarrollando básicamente herramientas de seguimiento de esta vulnerabilidad de la población a riesgos ambientales. Ya sin más dilación vamos a dar paso a la doctora Angeluccetti.
Thank you for having invited ITHACA at this international workshop. I'm sorry I was late, so I didn't consider that your campus was so big, so it took me 20 minutes from the metro station till here, so I didn't have time to say hello before the presentation still. So as it was said, at ITHACA, which is a research center based in Torino, we are collaborating with the European Commission on many projects, but we've also monitoring systems that we've developed internally. And one of these is this extreme rainfall detection system, which is based on near real-time measurements. And I'm going to present to you this one today. This extreme rainfall detection system monitors and forecasts exceptional rainfall events. This can be in the form of hurricanes, cyclones and tropical storms, and can trigger, of course, floods and flash floods. The whole system is deployed on the web through a WebGIS application that each of you can consult if you want. And this system was developed entirely in an open source environment. We have the developers at ITHACA, so we used their knowledge to build this system, to deploy it on the web. So this system was improved in the past 2 years for the main reason that it was using the NASA TRMM TMPA 3-hourly data, and this instrument has shut down. So I'm talking here about satellite rainfall measurements. So we had to improve the system in the sense that we did have to use another input data, and we take the chance to improve also the extreme rainfall detection methodology. It was based, as I said, on the NASA TRMM TMPA data, and then it performed a rainfall amount evaluation. Then on the basis of rainfall thresholds, it gave then alerts that identify areas potentially affected by hydrological disasters. I'm saying potentially affected because the system only monitors the rainfall, so we can't be sure at the actual stage if this produces or not a flood event on the ground. So these are potential floods that we detect. So as I said, the TRMM mission has come to an end, and then we had to decide what data to use instead. The new input data that was selected for the system was the NASA GPM IMERG products. The temporal coverage is from 12 March 2014 to nowadays. So, of course, the time series is not that long. The temporal resolution is 30 minutes, which is quite interesting. The spatial coverage is from 60 degrees north to 60 degrees south, and with the spatial resolution of 0.1 degrees, which is, again, quite interesting, of course, if we consider a global monitoring system. I'm not talking here about local applications, even though this system, the whole system could be downscaled. This input data is provided in 3 different versions. An early run, which is provided 4 hours after the measurement itself, a late run, which is provided 12 hours later, and then a final run, which is provided 3 months later with considerable corrections. For the reason that we want to give in-time alert, of course the final run had to be excluded, and then we work on the accuracy, on evaluating the accuracy of the early and the late run products, which are good, of course, for a near real-time flood risk monitoring applications. And this is particularly true where we don't have rain gauge available. So the first step was to evaluate the accuracy of these satellite-derived products compared to rain gauge data. These early and late products were compared with rain gauge data in 50 locations distributed worldwide that represent different climatic zones. And this evaluation was conducted between March 2014 and April 2017. As I said, the time series is not that long because of the nature of the satellite data itself. For every of this location, both the bias and the mean absolute error were calculated, and you have represented here in these 2 graphs the early data with the orange box plots and the late data with the red box plots. So the bias were calculated, as you can see, in the formulas, and the mean absolute error too. And this was done for a set of aggregation intervals that you can see on the x-axis. We wanted to... So the final aim of this accuracy evaluation was to decide what interval is best suited for the use in this system, and it is not affected by too big errors, of course. So we identified the 12 hours interval as a threshold to be used in this system. As you can see, from 12 hours aggregation interval onwards, we have bias that are less than minus 0.5 millimeters per hour, and then mean absolute error also that are a little bit over 0.5 millimeters per hour. So we decided that this 12 hours aggregation interval was the smallest one to be used in this system. Again, for each location and for each aggregation interval, a contingency table was produced in which we have reported the correct negatives, so both rain gauge and satellite data are null, the misses, where the rain gauge is non-null and the satellite are null, and the false alarms, where the rain gauge is null and the satellite is non-null, and then the hits, so when estimated events and observed events are both satisfied. So what we could do is calculate the false alarm ratio. It means that it's a combination of false alarms and hits. And we can see that for aggregation intervals higher than 12 hours, we have false alarm ratio that are considered acceptable. I mean acceptable because they are still quite big if you see the figures. So it's more than it's between 0.4 and 0.5. But still, we wanted to consider these 12 hours aggregation interval, for it is interesting for flood detection applications. And we could also, always exploiting the contingency table, we could also calculate the probability of detection, which is a combination of hits and misses. And again, for aggregation intervals of more than 12 hours, we have an acceptable probability of detection. So for 12 hours, this is between 0.7 and 0.8. But for 24 and so on, 48, it goes over 0.8, so it's quite a good probability of detection. Again, considering that we are working with satellite data on a global extent, so there are some limitations that are inherent to this kind of system. So this accuracy evaluation is summarized in here with the 4 graphs. The bias, the mean absolute error, the false alarm ratio, and the probability of detection. We can say a few things by looking at these graphs. As I said, the 12-hour intervals is considered acceptable. For intervals smaller than these 12 hours, we have 2 high value of bias, of mean absolute error, and of false alarm ratio and probability of the detection. And we can also see that the early and late data compares quite similarly for our application. So there's no point in using a late data for which we could consult the database of the MDAT, the Relief Web, and the Flood List, which are worldwide disaster databases. The MDAT in specific has in it all the natural disasters. The Relief Web 2 and the Flood List is specific to floods. Between these 85 countries, 63 of those were hit at least once by a hydrological disaster, and 22 countries didn't have any record in these databases. Overall, we analyzed 211 disasters. We did analyze the aggregation intervals separately. So for the set that you can see there, 12, 40, 24, 48, 72, and 96 hours. So the concept that is behind the system is the concept of threshold. So we want to identify the amount of precipitation that is needed to trigger a flood, so to trigger a potential flood. And we did this by comparing, by using actual disasters, actual floods that were reported in this disaster databases. So what we did is to develop and produce a set of threshold masks for each aggregation interval, in which we decided to consider as threshold a percentage of the mean annual precipitation that was calculated using the GPCC monthly products, so by using the rain gauge net, which is quite well established. We also did use of lower and upper bounds, so we forced the values that were less a certain value and over a certain value to the lower and the upper limits, and to see how, and we saw how this performed. So for each of these masks, we count the number of identified events that we could spot with the thresholds. So as I said, we use the mean annual precipitation calculated using the 10 years of GPCC monthly monitoring products. So as I said, for each of the simulation, the identified events were counted, and also the ratio between the false alarms and the identified events. We then selected the best performing threshold mask for each of the aggregation interval, And then on the basis of this, we can produce near real-time alerts. Here you have a screenshot of our WebGIS application, in which you can see on the very left the accumulated near real-time. You can select in this application which aggregation interval you want to look at. You can download the data, and most importantly, you can see in the right part also the alerts are provided in the system. So, as I said, the system that automatically downloads the latest, every 30 minutes, the latest GPM IMER data, applies the threshold for each of the aggregation interval, and it calculates, of course, the near real-time cumulated rainfall. It applies the thresholds, and it is able then to give near real-time alerts on the basis of these thresholds that are applied to each of the aggregation intervals. The improvements, the system that was based on the TRMM provided alerts and monitoring products every 3 hours. Now we provide alerts every hour. The spatial resolution was 0.25 degrees, and it is now 0.1 degrees, so quite a considerable improvement. And the spatial coverage too has been extended a little bit by 10 degrees north and south. Also, from the point of view of the threshold methodology, the system was based on only one threshold value for every aggregation interval that was multiplied by a mask of coefficients that were dependent on the Köppen climate classification. But now we have, for each of the aggregation intervals, a threshold mask that is characterized by 1 degree spatial resolution. So again, quite a considerable improvement from the point of view also of the threshold concept. From the point of view of the identified events, there was an improvement from 64% to 77%, which might not be considered such a good statistic, but still, if you consider that we are working at a global extent, it can be considered in a way acceptable. So the next steps we are thinking about for going forward are research of a forecast rainfall estimation. We have already identified the data that we want to use in the system, and that will be the global forecast system. That we would like to then we would like to develop a threshold methodology that will be calibrated on the forecast rainfall estimation. We wanted to insert an evaluation of the affected population, and we want to insert data maps of active cyclone tracks, and most importantly, a flooded areas evaluation, which will need, of course, topography data to be inserted in the system. And from the point of view of the system, the local applications of such a system, as I said, it will be, of course, necessary to take into account the downscale of the GPM data themselves. For instance, for applications that could be interesting for the Balearic Islands, we would need to downscale the data, but it's not impossible. There are studies that provide all the background research for this. And of course, as I said, it will be interesting also on the local level to integrate topographic data, and insert also soil moisture data into the system to understand better the probability of this extreme rainfall to trigger actually a flood event, a flood or a flash flood one. And for instance, it would be very interesting to link the threshold with seasonality, which is not done right now. So there's no seasonality took into account, and it will be good for have better hints on flood detection. So I think I'm done with the presentation, and I'm open to every question. But please consider that I'm not the developer of the system, so don't go too much into the details of the system itself, but I can give you the email and contacts of the developer. Thank you very much.